So the last time, we had completed our first hypothesis test. What was it about? Who were we? Who were we pretending to be last time? If you remember. If anybody wasn't here last time, I've got some data sheets. Who needs a data sheet? There's a big one. Everybody's got one. Good. What hypothesis tests? What claim did we test last time? Do you remember?
Do you remember?
Oh, that's what I said.
Do you remember also?
Flu vaccine! Boom! We had a flu vaccine we're looking at. Let's slide this up for a second. Who usually gets sick?
Good morning, stay well.
Who usually gets sick? What percent of folks? 12%. 12% usually get sick. 12% usually get sick. I want to get back into this because I think it was Rosie or Kaylee, I forget who asked me a very good question about the margin of error and the 10.1% that we got in our sample. Yeah, and I've never got around to answering that properly, I don't think. I want to answer that today. So we run a study. We create what we think is a flu vaccine, and we want to market this thing. You know, we get out there, but we got to see if it works first. So we do a sample of how many? 1,000 people. 101 get sick. So we end up with a p-hat value of 10.1% with a sample size of 1,000. And this is important. This guy right here is important. You can't just report that it's a p-hat value of 10.1%. You have to note that there's also 1,000 in the sample. And we'll come back to why that's important momentarily. Because otherwise, well, we're going to answer. Whoever asked that question yesterday, I apologize for not getting back to it. We'll get back to it today.
The question that I don't know if this is the one you're talking about, but I asked, so basically if more than this percent don't get sick, then it's still valid.
Exactly, and the thing is that cutoff value changes depending on this. That was, I remember you saying like 11.9999, I'm like, that could even be valid. Much to Jesse's consternation, that could be valid if you have, say, 80,000 in your sample. But this is where technology is going to help us kind of play. But let's revisit this one. Because I created this 4-step process for hypothesis testing. Just so you know, your textbook has more than 4 steps. I added a note to the homework sheet for this section that explains it has like 7 or 8 steps, which are fantastic, except a lot of their steps are just different versions of mine, if that makes sense. So my step 1, and this seems to work for a lot of students when they're understanding the process of hypothesis testing for the first time, is to set up your hypotheses you're actually trying to test. So you're going to have a null and you're going to have a research. All right? What are we testing? What are we testing? Go ahead, be brave. The effectiveness, good. How are we going to know if this thing's effective? Lindsay's 100% correct. How are we going to know if this thing's effective? I'll imagine how ridiculous that face looks with this hair. How are we going to know if this thing's effective? What's going to happen?
By how many people get sick?
Right! This is who usually gets sick. If the vaccine's effective, who's going to get sick?
Less than 12% of people.
Just less than. Perfect. Just less than 12% of people. Less than 12%. And P, by definition, is the variable, the percentage of those who get sick on the vaccine. Percent who get sick on the vaccine. If that's a sentence.
I'm not sure. If you guys speak a different version of English over there, start like the mother's tongue. That's kind of disgusting, isn't it? Mother's tongue.
Anyway, what's the null? What's the null? Remember, there's a technical and then there's also a conventional way of writing it. What's the technical? What would you have to write technically? And of course, I would accept this being a math guy. Good, more than or equal to. Kayla, absolutely, absolutely. You can totally write greater than or equal to 12%. You can and that's 100% correct. Because if you're trying to show the vaccine is effective, the opposite of that is ineffective. And the opposite of effective means either stays the same or it gets worse. Which potentially could happen anytime you're messing with somebody's immune system. That you could potentially run the risk of making it even worse. But by convention, very often, it's just written as P equals 12%. Just so you know. Just so you know. You'll often see that in the research. Even though this sign up here generally is always the opposite of this. Cool. Gesundheit. Fair enough? Fair enough, we're good, okay. So, we then crunch the numbers using the formulas. We're never gonna do that again. Because I don't want to get hung up in that computation. But there are two things I always want. Once you have your claim, and once you have your data, which is gonna look something like this, you're gonna run the machine and get the results out. And the results I want in step 2 and step 3 are what's called a test statistic and a p-value. And this will always be, I'm always going to ask you these two things. Why am I always going to ask you these two things? Eventually you're going to realize that if you know one, you can kind of have an idea about the other one. In other words, they're kind of redundant. If you know that the p-value is less than 5%, you know the test statistic was extreme enough to be significantly different. And if you know the p-value is greater than 5%, you know it wasn't. So it almost seems like, why not just give the p-value? That's a very good question. I have an okay answer. But it's more of a trying to prep you for the outside world answer. Because in research, they still give test statistics with p-values. Still, when you read research studies, very often, I pulled them out of the handout I gave you guys last time when I just gave you the research studies. I extracted a lot from that. I took out all the test statistics. They still have them. What they usually do is put, z equals blah, 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 comma, p less than 5%. Or z equals 0.62, p greater than 5%. P equals 1.12, p equals 0.33, or something along those lines. I like that because it lets you know what they did. If they just give you a p-value, you have no idea what test they ran. The test statistic tells you very often what test was run. It'll tell you if it was a bell curve z test, a bell curve t test, later on a skewed f test or a skewed chi-square test. There's all kinds of different clues that the test statistic gives. So I kind of like that they do tell you which statistic is used. But even if we didn't need to fact check them, they still use it. So I want to make sure that you guys get in the habit of writing those things down. Okay, perfect. What was our test statistic? Do you remember? I don't.
Remember. That's better. Do you remember? And what was this variable? Because we'll be very picky about that too. What variable?
Negative 1.85.
Very nice. I trust you. I don't remember. It's a long night.
What variable? That's the value. But what is that? What equals z? That's the one. That's the one. Z equals negative 1.85. Friends, was that extreme enough to get us into a p-value range where something happened? I.e., what was the p-value? I don't remember. It looks like this is far enough out to be less than 5%.
3.2.
3.2%? Beautiful.
Or 3.22.
That's cool. As long as, basically, and this is kind of nice too in this class, the TI is going to give you the p-value, the actual calculated p-value. Feel free if you want to just put p is less than 5%. Because that's what you're checking for. You're checking to see if it's outside of the 5%. Or you're checking to see if it's in that 5% interval. Why do we care if it's in the 5% interval? Why do we care? Murmuring. I love to hear murmuring because it's always right here from the. What are you going to do? It's good. I'm going to do the hair.
Because it shows something has changed.
Oh, something has changed.
That's quite nice.
What has changed? Huh? What has changed? I love that. It's perfect. What has changed, friends?
Let's be more sick.
Aha! We were expecting what percent to get sick? 12%. So we were set up to accept this. We were set up to accept this at 12% right here. And we allow variation around that 12%. How come? How come, friends? It's got to be a margin of error because we took a what? Yes, we have to go 95% confidence around our test statistic. So our test statistic comes back, right? We have to build that margin of error. But even before we start, this is the neat part about hypothesis tests. Before we even start, we built a margin of error around the 12%. And we say, here comes our data, 10.1%. Now I can't tell by just looking at that, 10.1%, whether or not that's close or far from 12.1. I know it's less. So I know my sample is indicating people aren't getting sicker than 12%. They're definitely on the low end of 12%. But the question is how low? How low? Somewhere down here, we spent some time last time talking about this, somewhere down here there is a z value called a critical value. A critical value that...
Whoa.
There's a critical value beyond which we put our hands up and go, wait a minute, something has changed. If we get below that cutoff, something has changed. And this tells us the location on the horizontal axis if we change the 12% to a 0. Why do we change it to a 0? Remind me why we change that to a 0.
Since your baseline, your average.
Exactly. We can normalize any curve back to 0. We did this in 243 all the time. Because I gave you the program. Remember what that program in 243 I gave you was called? At the very end there? Started with an S. Ended with a T normal. That's the one. Normal. The stands for standard. Standard normal. Because any curve that you want can be knocked down and put on that one right there. So the question then becomes, where did we land here? Well, rather than having you guys run to your program, that's where the p-value comes out. The p-value of 3% means you landed somewhere south or left of that critical value. So you landed out here. This area, 3.2%. There's your p-value. There's your p-value. So something has changed, correct? Now, your book, and I haven't gotten around to editing this yet, your book makes you write the conclusions out. And eventually I want to do that as well. And if I can get time between now and Tuesday, I'm going to try to get this done for you. But for step 4, I always ask the same thing at step 4. Write a clear, correct, contextual, concise conclusion that a non-statistician can understand. But until we get really, really good at knowing how to phrase that, I'm going to have you guys do a circle the correct choice thing. So here, I'm going to write it out for you. It either appears or does not appear that the flu, no E, vaccine lowers flu rates, no E. God bless us.
This English is a tricky language, you know. Some of these.
And your job is going to be, for at least for the next couple weeks, circle the correct thing in parentheses. Your book doesn't do this, and I will, given time on Monday, get in and actually change all of the part step 4 so that it does do this. I haven't gotten into it yet. So your job for right now is just to circle which of those two is correct. So which one are we going to circle? We're going to circle appears. We're going to circle appears. Because we got ourselves a positive test result. And a positive test result means something changed. Lindsay said correctly. How's that? That's a hypothesis test, friends. That's a hypothesis test. I want to come back to this, but I also want to answer Kaylee's question about sample size as well. Let's make sure this is kind of we just did that in like 3 minutes, but that was what we spent about an hour on yesterday. I want to make sure that quick little recap kind of shakes some fruit loose. Oh yeah, I remember that. I remember that. It's kind of ish. It's early. I know.
I don't know. I feel.
Jack, go.
What's the calculator function again?
Good. Let's do it right now because I want to use that to help answer Kaylee's question as well.
What is that her question?
Say that again.
What was her question?
Her question was, what happens? How close does this have to be to that until it's not significant anymore? And it's a loaded question because it can vary depending on sample size. But Jack's question as well. Jack's question as well is what's the calculator function we use to generate these? And that's definitely worth looking at again. So let's kill 2 birds with 1 stone. I hate that phrase. Well, I just said, used to be a vegetarian for God's sake. You know, killing. Alright. Let's fire this thing up. We see that okay in the screen?
Yep.
Alright. So, that was beautiful. Those were guesses on my weight yesterday. I said, guess my weight, 240. That just been 243 for you guys last year. 140 to 185. 140 to 185. Wow. 140. I know way that's his freshman year of high school. Good Lord, 140. It's okay. Anyway, the news is who they are today. 105. 107. Anyway, so where that is, Jack? Stat tests. Everything we're going to use is in stat tests this year, except for a couple programs I've written for you guys. Down to 1 prop z test. Just like 1 prop z int, but 1 prop z test instead. 1 prop z test, boom. And then it's just a matter of setting up the screen to reflect your data. to reflect your data. So you notice 0.12, 101 over out of 1,000. And the part that's going to get us for a little while, and that's why I've got a whole bunch of exercises planned for today, is what to put here. Everybody figures this out very, very quickly. There's a reason I have you write the hypotheses out. There's a reason. Now, you never see hypotheses in research journals. You see them written out in words. You see them written out in words. Or at least you can derive what they tested when you actually follow up the reading. Caffeine lowers heart rate during submax exercise. Well, you know what the hypotheses are. That we actually extracted them last week when we did that problem. But this value here is whatever the value you're testing against is. This is the kicker down here. This whole line right here essentially is what is the sign in the research hypothesis. That's all you're looking at there. What is the sign in the research hypothesis? I'm just giving myself an idea of anything I should do. I should make a graphic that goes along with this. Sorry, one second. Let me show you this one myself. So we're picking less than, and this is one of those things, I can't help with this. I've tried for almost 20 years. If inequality signs are giving you grief, I can't think of anything clever to help make more sense. I've been trying. The one that keeps getting mentioned in class is the alligators, and the alligators don't seem to help. Like if you get the alligators now, that's great, but I've tried to explain it with the alligators, and that doesn't make you get it. So this is why it's important to write them out correctly in your hypotheses. Then you either have calculate or draw. We went right to draw last time, and the reason we went right to draw is because that gives you everything, that gives you everything you need. If you go to calculate, you'll see what you'll get. You'll get what you need, but you'll get other stuff as well. So you'll get your test statistic, and you get your p-value, but you also get your p-hat, which is your sample statistic, and you'll get your sample size, which seems a little silly, because you can do those things on your own, and you don't need to report them back in a hypothesis test. Although sometimes you'll want to see what p-hat is. You actually want to know how close that is to the hypothesized proportion. But anyway, we usually go with draw, so we'll do that one next. And I swear I'm getting to your question, Kelly.
No, it's okay.
So there you go. There is your p-value. I like this for a couple reasons. Number one, it gives you exactly what you need. Number one. Number two, it gives you a visual of where your p-value actually is. That's fantastic. Some downsides, it doesn't tell you that that's equal to 0 and that represents 12%. But we'll do that enough in class together that you'll pick that up. I won't let you, I'll hammer it in your head, basically. And it's just nice to have that visual of basically where the interval is. The interval's here. I wish the TI actually put a critical cutoff here and then showed that somehow differently. But, I wish for a lot of things the TI would do it. It doesn't. Now, Kelly's question. Right, 10.1%. How close, make sure I'm paraphrasing this correctly, how close can that be to 12%? Or how far away can it be until it's significant?
Wait, what's the 10.1%?
That's the sample statistic that is right there. So 12% is here, our 10.1 is here, and our p-value is whatever that is or more extreme. So it's what came back in our sample. 101 out of 1,000, 10.1% got sick.
I see.
And we're comparing it to 12.
Okay.
And I remember when I asked the question in class last time, I said, is the vaccine working? A whole bunch of you said no, right? Half of you said yes, half of you said no. And then Will busted a confidence interval out.
Right.
And that kind of indicated that maybe it was.
Yeah.
And the question is, the reason why a bunch of you said no, knowingly, is that 10.1 is pretty close to 12. It's within 2 percentage points, which is a pretty small margin of error. And it makes you wonder, like, wow. But the thing about margins of error is they vary with sample size. So check this out, friends, check this out. Go back to stat tests. Go back to stat tests. Grab one prop z-test again. And let's change the sample size, but maintain p-hat. So what I'm going to do is I'm going to maintain 10.1%. But we're going to change the sample and the x's and the n values so that n gets either bigger or smaller. Let's make it get bigger first. Make it get bigger first. So let's make it get bigger. Let's make it 2,000. Let's say we infected twice as many people. I say infected. We gave twice as many people the vaccine. I guess it is kind of an infection, isn't it? Close. It's disgusting. How many would have to get sick to maintain a 10.1% infection rate? 202. 2. Oh, 2. Let's draw it. Now, you're going to notice some interesting stuff. Here she comes. What do you notice?
P-value is tiny.
The p-value got even smaller. What else got smaller? What else got smaller? Somebody be brave. I hear it back there. Eric, is that you? I'm going to pick on you.
No, but I think it's the Z.
The z statistic changed too, didn't it? Wasn't it negative 1 point something? And now it's negative 2. It's almost 3 standard deviations down. How the hell did that happen? How the hell did that happen? I'm asking a 243 question here. So if you don't know the answer to it right away, that's okay. Leave that up here. I'm going to slide that camera over this way. You guys did fantastic questions today, Kaylee. This is part of the answer to it.
I think I guess I'm so confused about the 10.1.
Mm-hmm.
I guess I know that's the number of people that got sick out of 1,000.
It's the percentage that got sick out of 1,000, right? Uh-huh.
But my original question was, if 12% of people are getting sick from the flu virus,
Yes.
is it considered, is it working if only 11.999?
We're getting to that. I'm getting to that. What
Okay.
I'm doing is I'm letting the sample sizes go like this to show you that sometimes it is and sometimes it's not.
Got it.
Hold that thought, okay?
Got it.
Here's first of all why that changed. Because if you understand why that changed, my God, that's small. If you understand why that changed, your question will become much more clear.
Okay.
So here, and the TI does a crappy job of showing this, just so you know. It doesn't show this very well at all. Here are all the standard normal curves that could possibly exist for this experiment. So they're all over the place, because they can be 12%, 11%, 10%, 9%. We deal with that by making them all standardized around 0. That makes it very easy. And that corresponds to 12%. Fair enough so far? Now, here's the kicker. Somewhere down here is our p-hat value of 10.1%. This is the hypothesized little p. We're saying that we think it's 12% because we're assuming it's ineffective when we go into the experiment. But here's the deal, and this is the part that the TI doesn't indicate very well in its images. When you have a sample of size 1,000, the bell curve might look something like that. Okay, this is where n equals 1,000. Now, when n equals 1,000, we end up with that p-value over here of about 3%, right? Ish, 3.2% I think is what it was. It's small. It's small. 3%. But when we redo the study with a sample size of 2,000, and think about the assumption I'm making right here. I'm assuming that the proportion stays at 10.1% in my sample that gets sick. I'm assuming that happens. I have no proof that that actually will happen, but let's say that it does, because I'm trying to answer your question with 10.1%. What is that sampling curve going to look like? Either in words, or if you're feeling brave, come draw it. What is that sampling curve going to look like? Taller and thinner, which means it's going to come in lower and take longer to rocket up like that. What happens when that happens? Well, the test statistic is still over here. But how much area did we trap here? I can't read it anymore, it's too small. 0.45%.
0.00.
Right, 0.0045, which is about half of 1%,
Okay, yeah.
right? About 0.5%, which seems more significant, doesn't it? It's less than 1%. We're now, where this is outside of 2 standard deviations, this is outside of 3. So in other words, the same proportion, 10.1, is more significant when more people demonstrate it than 10.1% is when only 1,000 people demonstrate it. And that's the idea. This goes back to Jesse's point. This is the same, I hate to sound redundant, I hope I'm not sounding too redundant, but it's the same thing that happens with margins of error in confidence intervals. When your sample size increase, the margins of error shrink. That's what's happening to the curves. And if you were to survey 5,000 people or 10,000 people and still maintain a 10.1% p-hat value, these curves are going to get even skinnier and taller, which makes that even more extreme. Don't take my word for it. Go find out. This is where technology is our friend. This is where we like technology. Well, we always like technology, when it's working anyway. Slide that back. Set it on the screen again. Are you guys slightly remembering this from 243-ish? Ish. Starting to come back, yes, much to your consternation. Roll it. So if you run it again, and then get focused. Woo! I just did my hair, thank you. All right, run it again. So everything's the same, but let's do it out of 5,000 instead of 2,000. But we want to make, and this is a big if we maintain 10.1%. Okay? So 10.1% would be 505 out of 5,000. Same test, different numbers. Four standard deviations down, even more extreme. They just go up and say the p-value is 0. It's not 0. It's 0 to 4 decimals. It's 0.00000 and then something, but it's 0 to 4 decimals. It's pretty much 0, right? It's pretty much 0. Because 10.1%, you got to remember, statistical significance only exists when you're comparing a sample with a margin of error. In a parameter, if you're actually looking at parametric values, if you had them, 11.99 is less than 12. I don't know if it's practically important that it's less, but mathematically it is less than 12. Does that make sense, Caleb?
Yeah.
We're getting back to your question again. So 11.99 is less than 12, but we don't have parameter values, we have statistical values. And with the margins of error, this is telling us that the difference is statistically significant. Now, Kaylee's question is, suppose the p-hat value came back at 11.99. Okay, let's say it wasn't 10.1. Can we re-answer this question in a different way? Is that okay? Let's suppose the p-hat value came back at 11.9. 11.9. And the flu manufacturer said, hell yeah, 11.9, that's less than 12. Start selling it. Well, as the FDA, you want to check that, right? You want to check that. So let's check that. Let's check that. Stat tests. Same hypotheses, but here's the kicker. We had 11.9. 0.1, oops, sorry, wrong spot. 0.119 out of 1,000. Let's make it out of 1,000 first. That would be 11.9%, right? 119 out of 1,000?
Not decimal.
Oh, thank you. Oh, and thank you, Will, for that. Will actually give you an error if you put a decimal in there. My apologies. Thank you. If you try to put a decimal in for x, it gets upset for some reason. You have to round them off to the nearest whole number. Thank you. Yes, 119x out of 1,000. What do you think? Will the FDA say, go ahead and market your flu vaccine? What do you think? It's less. It's less. Look, I can see the halfway point. I can see 0. It's less. What's the FDA going to tell you? The FDA is going to tell you it's essentially a coin flip if they get sick or not with your vaccine. It's just below a coin flip, but basically it's a coin flip. Is that a big or small p-value? What do big p-values tell us? Which means if nothing's changed, what's the flu rate for those taking the vaccine?
Same what it was.
The same as general population, which is 12%. So when you got a big p-value, which hypotheses do you believe? There's a table there. Which hypothesis do you believe when you got a big p-value? You believe the null. So you see, there's no reason to think that the flu vaccine is actually lowering flu rates. Now, Kaylee, we're not done answering your question yet. Suppose this drug company is tenacious. They want their shareholders happy. They want to sell this product, and they think it works. They're convinced that it works, so they go back out. They go back out and they take 1,000 more people, and they sample 1,000 more. And lo and behold, they get the exact same p-hat value on the way back. Let's test it again. Okay? We're still testing against 12%, which, as Eric pointed out last time, should have a margin of error. But why do I say we don't worry about it?
You didn't have to refresh me on that.
Oh, that's okay. You asked a very, very good question. Because it's been a long 2 days, Roll. I know about it. So, it has a margin of error, but we've seen it for so long and for so many sample sizes, it's essentially shrunk to 0. So you can treat it as though it doesn't have one, because it's basically not there. Does that make sense?
Yeah.
You're essentially testing a parameter value at that point. But your statistic is not a parameter. It's got a margin of error. So we're going to go to 2,000 people, but we're going to maintain the proportion, which means how many got sick? Well, that was the 10.1%. I want to test 11.9%.
Still only.
So it's just double that, right? So 238.
Oh,
I'm testing 11.9%.
I see.
I'm trying to maintain a p hat value that's larger, but still less.
Okay.
Because Kaylee's question is a good one. How close can it get until it's significant? And it varies. So let's do 238. Remember what the old p-value was? When it was out of 1,000, it was about 0.46, 46%, almost a coin flip. Let's run it again, now that it's out of 2,000. What do you notice? It's not wickedly extreme, but didn't it go down?
Slightly.
Slightly, correct? So we go to the FDA. Oh, I see more space there. What is the FDA going to tell you?
Same thing.
They're going to tell you the exact same thing. It's still a coin flip. So what does this company do? They're tenacious. They're going to go out and they're going to get 10,000 people, as the FDA often does. Sometimes they even go higher than that. They're going to get 10,000 people. And that's going to be 1,190. Yes? 1,190. Cool. We're maintaining 11.9. It went down again. Because it's getting more significant. But it's not significant enough yet. So the question is, how far out will we have to go until it actually is significant? I don't know, but you can get to it. So even 11.9 can be shown to be statistically significantly less than 12% if your sample size is big enough and the curve is tall and skinny enough. Does that make sense? That was such a good question, it just didn't have a quick answer.
No, that's okay.
And it's such a good question because you can make any statistic significantly different than a given parameter given a large enough sample size. Of course, you also have to maintain that 11.9%. It could be that your flu vaccine really isn't working, and the next time you run it, it comes back at 12.2%. And it averages over time to 12%, at which point you realize you spent a lot of money to make water, essentially. You're going to ask a question, Kelly. Go ahead.
Yeah, so what will the Z and the P values look like if it is significant? Will the P fit within that Z value?
That's a fantastic question. What will the Z and P look like when it becomes significant? Do you remember what the P will look like? Say yes.
Yeah.
The P will be
Under 5.
under 5%. What will the Z be? This is a grade 243 question, actually. What will the Z have to be? Ish.
Over 2.
Actually, for a two-tailed test, yes. So, for example, if we were testing a two-tailed test, which we'll do at the end of the day, I'm going to test what's called a two-tailed test. This is a one-tailed test, though. Now, why am I saying a two-tailed test? Why do I keep saying two tails? Two tails. Two tails implies you're chopping 95% in the middle, which puts 2.5% on either side, which is essentially a -2 and +2. So yes, for a two-tailed test, it would be -2 and or +2. But for a one-tailed test, you have to take all this spare area over here and move it over here, which shoves it this way a smidge. It ends up being around -1.6, I think. I can give you a more precise answer if you want by running my normal program and doing a backwards problem that shades left 5%. The z-score you're looking for there, -1.64. That's kind of your cutoff critical value. So if you get a z-score that's less than -1.64 or bigger than +1.64 on a one-tailed test, and I keep saying one-tail, we'll come back to that, I promise. On a one-tailed test, that's going to be significant.
So the first time we ran it, P was like 46%.
0.46, yeah.
0.46.
And the z was like -0.3,
Right, so
which puts it on this side.
if it was significant, the P value would be like 0.005 something.
Something like that, exactly. And with a percentage that close, 11.9 to 12, you're going to have hundreds of thousands, if not even millions of sample points to think that it's significant. I'm just saying, it can be done mathematically. Because all it is, believe it or not, and if you want to see it mathematically, all it's got to be is this. The test stat, ooh, that's not right. The test stat computation, and I'm not going to do this, but I'm going to do this to illustrate why you can get there. Your test stat calculation always looks the same. It's going to be your samples center minus your hypothesized center over that standard error. And that standard error looks like this. Don't memorize this at all, please. P and Q are based on your hypothesized center. N's your sample size, and P hat is that 0.119 we kept using in the sample. 0.119, 0.119. Well, all that's got to do is equal 1.64, and you're done. So you know what that is already, 0.119. You know that that's 0.12, 0.12, 0.88. N is variable. Solve that for n, and that tells you how big a sample you need to get significance at 11.9% p hat. I wouldn't be surprised if it's a million, because it's so close. But you can get there. Essentially, you need to get this guy to look basically like a straight up and down line. Because you have to think about it. You have to trap 95% of the area to this side of 11.9, which is right next to 0, essentially. But your job is to get it so far away from 0 via standard error. Because this is the difference between standard error and standard deviation. The standard deviation of the normal curve is 1. 0, -1, +1, -2, +2, -3, +3. The standard error fluctuates as sample sizes get bigger. You guys aren't excited about this assignment. It's okay, I understand. I understand. But the important thing is, there was a great question, very important question, that leads to the belief and the importance of replication of studies. How often have you heard in other classes, when you replicate a study, the results get more believable, when you can replicate a study under similar conditions? You're explaining why. It's becoming more statistically significant every time you replicate a study under similar conditions and you get the same result, essentially. It becomes more believable because it becomes more statistically significant. Fair?
Okay, you have that glaze. I'll tell you what, come back and do some more. Jesus. Where are the outfits? I see a tie. I need to borrow a scarf.
I almost put a flag on today, actually. Lindsay had an American flag. I was like, I should wear that. I should wear that. But I don't know how people feel about that. People wearing flags. I don't know how people feel about it. I don't. I used to be a Boy Scout. I don't know if people get weird about the flag. I don't want to piss anybody off.